Welcome back, everyone, to this continued discussion of the theory and intuition behind support vector machines. In this lecture, we're really going to focus on the kernel trick and the mathematics behind support vector machines. Previously, we've really only discussed the intuition behind these methods. So what we're going to do now is briefly go over the general mathematics of how we build up to support vector machines, and we'll also discuss how the mathematics is related to the scikit-learn class calls. We'll begin with a brief review of using margin-based classifiers, slowly expanding from maximum margin classifier to a support vector classifier, and then finally using the kernel trick for support vector machines. Now, feel free to consider this an optional lecture, which you can replace with the relative reading. The background reading can be found in Chapter 9 of An Introduction to Statistical Learning. For a deep comprehensive overview of everything discussed, you could check out the original publication by Cortez and Vapnik called Support Vector Networks in the Machine Learning Journal. Now let's first talk about hyperplanes defined mathematically. Here, I can imagine a two-dimensional space with two features, x1 and x2. A hyperplane is just a line in two features, which means I could define this mathematically as the lines we've seen before, a beta naught for the intercept plus beta 1 times x1 plus beta 2 times x2, and set this equal to 0, and there's going to be some set of betas that is going to define this line. Now keep in mind, I could expand this to p number of dimensions, just continuing this where there's a single beta coefficient for every single feature. Now, this is the mathematical definition of a hyperplane for some p number of features. Let's talk about separating hyperplanes. The whole idea behind hyperplanes for support vector machines is that they're separating out the classes, which means I should start thinking about not just the hyperplane line itself, but the mathematical definitions of what I'm going to consider as a separating factor. So I want to consider the values that are above 0 are going to fall on one side of this hyperplane. Similarly, the values below 0 are going to fall on the other side of the hyperplane. So now I have a set of equations that is able to define what side of the hyperplane you fall on. The last consideration we need to make in order to mathematically define something like a max margin classifier are the data points themselves. Something to note here is that when we actually type this out mathematically, typically we show the actual feature points or data points as the transposed matrix of X. That is to say that x1 through n represents the number of data points, and 1 through p represents the number of features. So notice that this is transposed from the way that we typically write out our data in something like a Pandas data frame. It's the same data, just transposed so that in the columns are the rows and the rows are the columns. Again, 1 through n is the number of points themselves, 1 through p is the number of actual features. So in this case, we would have two features, x1 and x2, given the diagram on the right. And we would have 6 points. So 1 through 6 would be 1 through n. Now let's use all this information to mathematically define a max margin classifier. Recall that the whole purpose of a max margin classifier is to maximize m, where m is this margin extending from the hyperplane. So we're essentially trying to choose the best beta coefficients that can maximize this margin. But we do have some constraints. We're subject to these two constraints given the data set. So what does this actually mean? Well, all this means is that what we're trying to do is consider the data points here. In this case, we have 6 data points, or 1 through n. And what we want to do is make sure that we fulfill this subject requirement, where essentially the data points are either going to be equal to or greater than the margin, depending on what side of the margin they actually fall on. This essentially is just a mathematical way of saying that for a max margin classifier, no data points can actually be within the margin. We're also subject to this sum of squares for the beta coefficients being equal to 1. Now, this actually helps correspond to the other equation by determining that if you were to plug in the features values into the equation below, if you're subject to beta squared and the sum of those being equal to 1, then y of I multiplied by these beta coefficients times the feature value gives you the perpendicular distance from the point to the hyperplane, and it ensures that that distance is at least as large as the margin itself. This is just to say that with this constraint, we are able to mathematically calculate the orthogonal distance from any point to the hyperplane. And here we have the full definition, mathematically speaking, of a max margin classifier. Again, given this transposed matrix of data points, we want to figure out the beta coefficients that are going to maximize this m subject to these two equations, which essentially makes sure that the points are outside of those margins and are falling on the correct side of the margin given their class, and we're subject to this beta squared sum coefficient being equal to 1 in order to determine the orthogonal distance from the points to the hyperplane. Now let's move on to a support vector classifier. Recall, a support vector classifier is different from a maximum margin classifier because it does allow for misclassifications, essentially allowing for some number of points to fall within the margin. So we still want to maximize this margin, and we still want to make sure we're subject to the sum of beta squared being equal to 1 in order to be able to determine the orthogonal distance from the vectors to the hyperplane itself. But because this is a support vector classifier, I now allow for some error term. So notice I'm using epsilon, and this epsilon is a relationship between some set C value, where this C value is going to determine how many misclassifications you actually allow yourself. So it's pretty much the same equation, except now the margin has this error factor, or epsilon factor, determined by the sum of the epsilons being less than or equal to C, where the C can be provided by the user. And we're going to be able to use cross-validation to solve for the optimal C in order to maximize accuracy or maximize precision or recall, depending on what we're actually trying to optimize here. But this is the full definition of a support vector classifier. Essentially the same thing as a max margin classifier, but with these added constraints or addition of the fact that we can actually have misclassifications constrained by some value of C, and as C goes to 0, then we're actually back at a max margin classifier, essentially not allowing for any errors. Now, a quick note on this value of C. You should notice that the way we've defined it here mathematically, the larger the C value, the more errors we allow ourselves. In scikit-learn, due to the fact that they want to remain consistent across multiple models, they say C is a regularization parameter inversely proportional to the C shown in the equation here. That is all to say that mathematically speaking, in the equations we're showing here, as you increase C, you increase the number of misclassifications you allow. In scikit-learn, it's inversely proportional to the equation shown here. Obviously, that'll be more clear as we begin to experiment with scikit-learn, but it's just something to keep in mind, that the C in scikit-learn's documentation and class call for support vector machines is not exactly the same thing that I'm showing here in the equations, or that you will typically read when you're actually reading the equations for support vector machines. It's actually inversely proportional to C, and that's just because they want that regularization parameter to remain consistent across multiple models. Okay, so finally, let's move on to support vector machines and how we define these mathematically. Recall that we need to use support vector machines where we're not able to find any clearly separable hyperplane for our data points. Here, we have what looks like something we can't really separate with a line. We have a bunch of points in the middle and then another class surrounding it. So what we do, as we previously discussed, is transform this to some sort of higher dimension or feature space. So right now, I could have features x1, x2, all the way to xp number of features. And I could use something like a polynomial transformation using x1 and x1 squared, x2 and x2 squared, all the way to xp and xp squared, in order to try to figure out if there's a hyperplane in this larger feature space that will successfully be able to separate out these two classes. And I can still allow for misclassifications in this higher feature space. So again, what I want to do is maximize this margin, but now I have a lot more beta coefficients to consider depending on the feature space that I'm expanding this to. So if we just lay this out all mathematically, what we're doing here is we're adding the addition, for this simple case, of a square polynomial. Keep in mind, this is not a generalized support vector machine. I'm just showing the support vector machine that we previously showed where the expansion of the feature space was squared. Essentially one of the simplest support vector machines we can possibly do. So we're no longer just considering x1, x2, all the way to xp, but we are also considering the squared feature value. I still want to maximize my margin m, but now I have coefficients not just for the original features, but also coefficients for the squared features. And I am allowing for misclassifications, which you'll notice are actually in the subject to y of I, where it's greater than or equal to the margin times 1 minus epsilon, where epsilon is again defined by this user parameter c, essentially allowing for some misclassifications even in this higher feature space. So then this support vector machine, with the utilization of this larger feature space, would allow me to figure out how to separate the actual feature space in order to classify these points correctly, even beyond the constraint of the original features, since I'm now considering some larger feature space of things like x squared or x2 squared, etc. Now the main question that arises as we move on to a larger feature space is, how do we actually deal with this growing complexity? While we only showed a simple example of a polynomial degree of 2, it's very likely that for more complex datasets, we'll need to grow this polynomial to a much larger degree. And as the polynomial order grows larger, the number of computations necessary to solve for margins also grows, to a point where it may be infeasible to actually compute that many margin calculations. The answer to deal with this lies in the kernel trick, which makes use of the inner product of vectors. This is also known as the dot product. Before we show you how we can actually use the kernel trick with our support vector machine calculation, let's quickly review what a dot product or inner product actually represents. So here we're going to simplify a dot product to just be between two vectors. And recall that vectors can be more than just two dimensions, as shown here. It can be many, many dimensions. But for simplicity, we're just going to use this in a two-dimensional space. I have vector A and vector B. And the dot product or inner product between these two vectors is defined as the sum of each of their subcomponents multiplied together. That is to say, if I have two-dimensional vectors shown here, then there's a subcomponent along the x-axis and a subcomponent along the y-axis, which I could define as A1 and B1 along the x-axis, and then A2 and B2 along the y-axis. Then you can imagine that as we move on to three-dimensional vectors, four-dimensional vectors, etc., there will be subcomponents for each of those dimensions. And for the dot product, that would mean, in this particular case, the inner product or dot product between A and B would just be the sum of each of those subcomponents multiplied together. Now you may also remember from your math classes that this is not the only definition or mathematical notation for a dot product. The dot product can also be defined as the multiplication of the magnitude of each of the vectors multiplied by the cosine of the degree between them. Now why is this important to also note? Notice that if we start thinking of a dot product in this format, it's essentially a similarity between the vectors. So this is going to result in the same calculation as saying A1 times B1 plus A2 times B2. It's essentially another definition for the dot product. The reason this is useful is because with this production of cosine of theta, it's a similarity measurement between the vectors. You can think of this by considering extreme cases. Imagine that the degree between these was 0. Cosine of 0 is equal to 1, where that means the dot product is essentially the multiplication of the magnitude of vector A and vector B. That makes sense because if the degree was 0, that means both these vectors are pointing in the exact same direction, meaning that their degree or cosine theta is 100% similar, so it should be equal to 1. You'll also notice in the case that these two vectors are perpendicular or orthogonal to each other, cosine of 90 degrees, that would be equal to 0, meaning the inner product is equal to 0. And then, if they are pointing in exact opposite directions, that is cosine of 180 degrees, then we would have negative 1, essentially saying it's negative 1 times the magnitude of A and the magnitude of B. So clearly, we can think of this inner product as a similarity measurement. So let's now move on to discussing the kernel trick. We can think of a linear support vector classifier in terms of this inner product, where we can say that we have some function of x is equal to beta naught plus the sum of some alpha term times the inner product of each pair of training points, we essentially calculate the inner products of all pairs of training observations. And you can check out the reading in Chapter 9 of ISLR for a more in-depth look, or you can check out the publication from Cortez and Vapnik as well as why we're able to actually perform this calculation of inner products. But for now, kind of just take it as is that I'm able to rewrite a linear support vector classifier in terms of inner products. Now, since I'm able to calculate the inner products of all pairs of training observations multiplied by some alpha parameter, you'll realize that in this particular case, the alpha parameter is only non-zero for the support vectors. So let's back up a second and see if this makes sense. I just told you I can rewrite the linear support vector classifier using this equation, which says instead of calculating this beta coefficient times the feature value itself, I'm going to try to calculate this alpha multiplied by the inner product of all the pairs of training observations. But if I rewrite it this way, you'll soon realize that alpha is only non-zero for the support vectors, marked in yellow on that plot. Now, does that make sense? Well, intuitively speaking, it does. Recall the margin only depends on the support vectors. And from the margin's point of view, it doesn't really matter once you hit the support vector what vectors lie beyond it, because you're only defining that margin by the first support vectors it comes into contact with, which means you're already saving yourself a lot of computation by only having to worry about the support vectors, that is, the vectors that come into contact with the margin. Now, because of this, I can rewrite from I equals 1 all the way to n number of points, and instead only consider I set S, where S is a collection of the indices of these support points. Essentially the same equation, but I'm only considering the support vector points because we can show that alpha is only dependent on those supporting points, essentially not having to do as many calculations. Then comes the kernel function. So we're going to define a kernel function as a function k between two training points, training point I and training point I prime. And we can show that this is going to be equal to the following sum, x of I of j multiplied by x of I prime of j. And this should obviously look familiar because it looks like an inner product. And a kernel, you can think of it as a function that just quantifies the similarity of two observations. And we just talked about how the dot product and inner product is essentially a similarity measurement. That means if you begin to actually look at that linear support vector classifier equation, we define that using an inner product. So now I can use my relationship of an inner product being equal to the sum of these multiplications of each subcomponent in order to swap in my kernel function into this newly rewritten support vector classifier, essentially giving us a support vector machine, where I can easily swap in any kernel function I want, where again, the kernel function is essentially a similarity measurement. And there's actually many kernel functions to choose from. Here, we're showing the simplest kernel function, which is just a linear kernel. But I can also have a polynomial kernel. Notice I'm now just calculating this kernel function where I have a relationship between the kernel function and the degree of what I want to calculate, saving myself a lot of computation because I'm no longer actually computing calculations in the full feature space. I'm computing the kernel, which is an inner product. Another popular kernel is the radial basis kernel, or otherwise known as RBF, radial basis function. This is a much more complicated kernel, and in fact, if you try to actually compute this without using the inner products, it actually creates, in theory, an infinite number of computational comparisons. So the only way to mathematically do this is with a kernel function that is going to use the inner product. So the use of kernels as a replacement is known as the kernel trick, and that is what actually happens when we use support vector machines. We're able to rewrite that relationship from the support vector classifier in terms of an inner product. And then we have a variety of kernels to choose from that are essentially defined as similarity functions, which I can swap in wherever I see that inner product happening. And then kernels allow us to avoid computations in the enlarged feature space by only needing to perform computations for each distinct pair of training points, where I really only need to consider those support vectors themselves. The full details behind this can be found in section 9.3.2 in ISLR. Now, intuitively, what we've already seen is that inner products act as a measurement of similarity between vectors. And the best way I can intuitively explain support vector machines, in case you were a little unclear by the kernel trick, is that the use of kernels can be thought of as a measure of similarity between the original feature space and the enlarged feature space. So instead of having to actually perform the raw calculations in the enlarged feature space, I can say that kernels will give me a measure of similarity between the original feature space and the enlarged feature space and use the kernels to perform my calculations instead, saving me a lot of computational work in that enlarged feature space. Okay, now that we understand the theory and intuition behind support vector machines, let's move on to actually using them with code. I'll see you in the next lecture.